Steinhauer here, welcome back. In this video, we're going to be talking about the differences between luminosity and brightness. They're both related, of course, and they're both important to astronomy, but they are very different things. Luminosity, as we mentioned in the last video, is a measure of how intrinsically bright something is. It is how much energy an object is giving off per second. It has units of joules per second or watts. Apparent brightness is how bright something looks to you, and is not an intrinsic property of that object, because how bright an object appears to you depends both on how intrinsically bright that object is and how far away that object is from you. If you move an object that has the same brightness further away, it's going to appear fainter. They don't even have the same units, luminosity and apparent brightness, because apparent brightness depends on how much light is passing through some aperture, like your eye or hitting the earth or your telescope or whatever it is. And so apparent brightness actually has units of watts, which is joules per second, per area or per square meter. And so how are these two related, and how does that work is the topic of this video. So let's move on to the next one. Hopefully this will make it clear why the formula is what it is. We'll talk about the formula in a second, but this is important. If an object is radiating energy uniformly into space, then the energy that it generates and radiates away in a second, as that, let's take that energy that is generated in a specific second and watch it as it expands away from that object, right? You're spreading that whole amount of energy over a sphere whose distance is how far that sphere, how far that light has traveled in the time that it has gotten there, right? And so we can see here, if we have a light bulb at the center, after that light travels a meter, the energy that was generated in that second is spread over a area that is 1 meter, that has a radius of 1 meter, that is 1 meter away from that object. After 2 seconds, and so you can see the light that is traveling out in a particular spot might be filling this square, right? After, at 2 meters, that same energy is being spread over a sphere whose radius is twice as large. And so the same amount of energy that passed through the single square on the first sphere, on the second sphere, it is twice as big on each one of those sides. And so has an area now of 4 squares. The same amount of energy now spread over 4 squares. And at 3 meters away, that same amount of energy is now spread over an area that has a 3 by 3 grid of squares, 9. And in fact, this actually leads to the brightness, the relationship between the luminosity of an object and its brightness as a function of how far you are away from it. Because as that light spreads out, you're spreading it over a sphere. And the surface area of a sphere is 4 pi r squared. So the brightness has to go down proportionally to, that's what the symbol means, 1 over r squared. The bigger the distance, r being the distance from that object, gets, the smaller the brightness is, the fainter that object will look, simply by that factor. So that's the 1 over r squared law of light. You divide luminosity by area to get brightness, and that gives you the brightness formula. The brightness of an object is its luminosity divided by 4 pi times the distance to that object squared. Again, luminosity is how much energy per second the star is radiating away into space. 4 pi d squared, or 4 pi r squared, is the surface area of a sphere whose radius is the distance from that object. And so this is exactly what we were just talking about. Spreading the luminosity over a surface area that is a sphere centered on that object with radius distance gives you this formula, luminosity divided by 4 pi times the distance squared. So the cool thing is, this is useful in lots of ways, but one of the ways it's useful is you can turn this around and get distance, and you can get luminosity. If you know a star's this is how this generally works. We don't know the luminosity. If we know the brightness and the distance, we can calculate what the luminosity is. We can do some other algebra and solve this for distance. If we know a star's brightness and its luminosity, we can get the distance from it. And this is a way, in fact, it's a very common way to get distances to distant objects. If you happen to know what an object's intrinsic luminosity is, because maybe you know something about that object from some other source, you can always measure its brightness. And that says that standard candle, if you measure its brightness, you will get the actual distance to the object. That's the method of standard candles. If you know an object's luminosity, it has a standard brightness, it is a standard candle, then you can calculate the distance to that object. Okay, let's do one example, and then we'll call it quits for this video. The brightness of the sun at Earth is 1,300 watts per square meter. This is an important number. It's called the solar constant. If you want to generate energy by solar power, this is a number you're starting from, right? If you could capture all of the energy that's hitting the Earth, you would get 1,300 watts, joules of energy per second, for every square meter of solar panel that you have. Now, in practice, of course, solar panels are not 100% efficient. In fact, the best solar panels are on the order of 5% efficient these days. So you're not going to be able to actually store this much energy. But this is where you start from. Even a 100% efficient energy generation mechanism can only get to 1,300 watts per square meter. Here's the question, though. What is the brightness at Pluto? Pluto, whose semi-major axis is 40 astronomical units, is 40 times farther away from the sun than the Earth is. What is the brightness of the sun as seen from Pluto? So again, let's do we can make ratios. And when we make ratios, we don't need to worry about pi's and 4's, and all those things are going to go away. So we know that the distance to Pluto is 40 times the distance to Earth. That's one of our knowns. We know that the brightness at Earth is the luminosity of the sun divided by 4 pi times the distance to the Earth squared. And we know that the brightness at Pluto is the luminosity of the sun divided by 4 pi times the distance to Pluto squared. So we want to know what the brightness of Pluto is. Let's do a ratio. The brightness of Pluto divided by the brightness of the Earth is equal to, let's do Pluto first, L over 4 pi dp squared divided by the brightness of the Earth. And I can do 1 over L over 4 pi dE squared, or I can just flip this all around and do 4 pi dE squared divided by L. Since BE is on the bottom, I take my BE formula, brightness at Earth, and flip it around, and that's 1 over that thing. And again, things are going to cancel out here because I'm taking a ratio, and that's the whole point of this exercise. I've got the luminosity of the sun on the top and the bottom, those go away. I've got a 4 pi on the top and the bottom, those go away. And the only thing that's left now, I've got the distance of the Earth divided by the distance to Pluto, both squared. And I can take that square and bring it out and do the ratio first, dE over dP squared. Great. But I know what this ratio is. I know that dE over dP is 1 over 40. Let's do some algebra here to see how that works. If I divide both sides by dP, I get the dP canceling out over here. I also have to divide both sides by 40. Things cancel out over here, namely the 40, and I get dE over dP is equal to 1 over 40. And that I can plug in down here. So this becomes 1 over 40 quantity squared, or 1 over 40 squared. And 40 squared is 1,600. So this becomes 1 over 1,600. The sun is 1,600 times fainter at Pluto than it is at the Earth. And so if you multiply that times the actual brightness of the sun at Earth, 1,300 watts, this is less than a watt of energy from the sun at Pluto. This leads to the brightness of Pluto is equal to the brightness of Earth divided by 1600, or 0.81 watts per square meter. I'll give that a little red circle. But you don't actually have to do all of that math. If you understand how this equation works, in other words, that brightness goes down as 1 over the distance squared, all I needed to know was that Pluto's distance is 40 times farther away than the Earth, and I know that it must be fainter, therefore, by a factor of 1 over 40 squared, or 1 over 1600. So all I have to do is take that 1300 watts per square meter, divide it by 40 squared, or 1600, and I'll get the answer showing up.